Okay, so today we're getting deeper into proof, and we're learning more tools that we have available to us. Yesterday we started talking about how we have the postulates. That was the linear pair postulate, the segment addition postulate, and the angle addition postulate. And those should be listed on your proof tools that you're keeping a list of. Then we started also talking about some of the properties of equality that we can use to manipulate equations. So we talked about how, you can subtract the same thing from both sides to solve a problem, and that we called that the subtraction property of equality, right? We also said you can add the same thing to both sides and the equation stays equal, and that's the addition property of equality. And then we didn't write these down, but we mentioned the idea of a multiplication and division property as being a property that you could claim as a reason for doing other algebra solving techniques, right? If you're going to divide both sides, you can call it the division property of equality. If you're going to multiply both sides, you can call it the multiplicative property of equality. But now we're going to go through some other properties here that we didn't get to yesterday. So excuse me, the next one that we're going to do is called a reflexive property. So the reflexive property, it's almost silly, because it's a necessary step sometimes, but it seems just so obvious. And so what the reflexive property is, now you're going to want to think about reflexive, maybe think about like a reflection, because a reflexive property basically is when you want to state that something is equal to itself. Right? The reflexive property would be something is equal to itself. So let me see if I think I can do something here. Just a second. Let me see if I can type something here real quick, right? So if I wanted to say, 4 equals 4, that would be the reflexive property, right? Or x equals x. It's equal to itself. If I wanted to say the distance between point A, B is equal to the distance between points A, B, well, we can state that, but we'd have to give a reason why we're stating it, and the reason is the reflexive property, okay? So the measure of angle, let's see, the measure of angle, ABC is equal to the measure of angle ABC. Again, notice the reflexive property is really only used to state that something is equal to itself. So again, try to think about a reflection, right? Something that you would see on both sides of the mirror saying that it's equal to itself, okay? And that's the reflexive property. Okay, next we have the substitution property. So substitution property, think about a substitute teacher, okay? So with the substitute teacher, what we're going to do is we're going to say, let's see, I'm going to see if I can do this out here. So if I know that the teacher's out and I put in a substitute teacher that's equal, then you'll have the same exact educational experience. Now, I don't know if that's always the case. I hope that our substitute teachers are just as good as I am. But, in case they're not or whatever, this is how you would use the substitution property. Okay, the substitution property. First, you have two things that are equal. So let's say that like m is equal to x. Okay, so if we know that, and then let's say we had an equation that had m in it, so we'll say 3m plus 21 equals, I don't know, let's say 450, we'll just say. So now because m and x are equal, I can come down to this equation, and where I see m, what can I replace it with? Okay, so obviously I can replace it with x, and that means I could say 3x plus 21. So now again, I'm saying the same exact thing I said before, but I've taken out the m and I've replaced it with x. So sometimes you're going to want to do that. You're going to make a statement, and then you're going to say, all right, well, I want to make another statement, and I'm going to show that, I can still make this statement because of that statement, because I'm substituting. And anytime you have to, in order to do the substitution property, you have to do two things. First, you have to have a statement that shows that the two pieces you're going to substitute are equal. And second, you have to have a statement that shows you have an equation of some sort that you're going to substitute into. So if you have those two things, so we should probably number that. Number one, something that shows that the two parts are equal. And then number two, something that shows a statement of equality, an equation of some part, of some sort that includes one of those parts. And if you can do that, then you can make your third statement, and that third statement would be the use of the substitution property. Okay, so this is just an example where I'd say, okay, I know this and I know this. These are my P's, right? I'd say if m is equal to x and 3m plus 21 is equal to 450, that's P, my hypothesis, if, right? Then my conclusion, 3x plus 21 is equal to 450. And if I want to go from this hypothesis to this conclusion, I would use substitution. So because of that, a lot of times when people do substitution and they have a numbered list, right, they will often put in parentheses the numbers that they use to do the substitution. So I need to know, first, where did I show the two parts were equal? And second, what was the equation I'm substituting them in and out of? Okay? So that's how that normally goes, and that's the substitution property. So we have reflexive, remember something is equal to itself, and substitution, where two things are equal to each other and they are parts that are going to be swapped out in a subsequent equation. Okay? All right. Next we have the transitive property. Now, that trans is a funny root word, okay? When we say the transitive, we're often talking, I like to think about, you know, trans is a root word that kind of means crossing over. So for example, if we said you were on a transatlantic flight, you would be on a flight, a plane flight, that crosses over the Atlantic Ocean, right? Or sometimes we'll say a transcontinental flight, where we're going to fly from one edge of the continent and cross over to the other edge of the continent. So in order to use the transitive property, again, you're going to have to show a couple of things. So you're going to show that like A equals B. That would be like an example of one piece. And then we're going to say that B equals C. So now I would say that if A is equal to B and B is equal to C, then what do I know about A and C? Right? So then my statement here that I would make is I would say, well, A is equal to C, and that is the reason I would give, right? If this is the if part, the P, hypothesis, this is the Q part, conclusion, then I would say I can make this conclusion based on the transitive property of equality. Okay? And this is another one where you're basically going to have to show, you know, we usually try to show the parts that are involved. So I'm using A equals B, and I'm using B equals C, and those were the two lines of, you know, the given information that I used together to show A and C are equal to each other. The reason I say that is because when we do proofs in the future, they're not always going to be right next to each other, and they're not always going to be like this is 1, this is 2, and this is 3. Okay? So they may be buried in your proof somewhere. You may have first done some work to prove that A was equal to B and concluded that in line 4, and then concluded that B was equal to C in line 7, and then all of a sudden in line 8 or 9 or 10, you want to state that A is equal to C and go back and say, oh, I used line 4 and 7, right? You just want to be able to show where you did the transitive from. I'm going to draw another picture for you real quick. Just something that I like to do to just kind of, let's see if I can draw okay here. If I have a guy and he had, I don't know, let's say $45 in his pocket. So let's see if I can write this. 45, right? And then we had another guy, right? And he also had $45 in his pocket. we would say, because they both have $45, right, that the amount they have is equal, right? And then if this guy had a third guy, right, and he was also carrying some money around in his pocket, right, and I said the amount he has is the same as the amount this guy has, then what would I know about these two guys right here? Right? They would have to have the same as well, right? And a lot of times when we do this problem, like we don't actually, let me see if there's a, is there a, no, there's not really, oh, there's an erase button. Let me try this erase button. All right, let's, sorry, I didn't mean to do that. Okay, well, let's try it again real quick. A lot of times there's no money involved. There's no numbers even involved. We just say one person has equal amount as another person, right? And that person has an equal amount to a third person, right? And therefore, the conclusion, we say if these two are equal and these two are equal, then we would say, all right, then these two have to be equal, right? That is a use of the transitive. Notice just like that, we said transcontinental, right? Traveling like from LA to New York across the continent, right? We're passing over the middle part right here. So that's a way to kind of remember the transitive property, right? You're crossing over something. If I wanted to, let's say, think of it more like what you might see in a algebra class, I mean a geometry class, we might say that the distance between point A and point B, right? So here's A and point B, right? And then I might have some points C and D, we'll say. So C and D, right? And now I want to prove also E and F. So here's E and F. So a lot of times it'll just be written that, you know, like AB is equal to CD. And maybe you have out there that CD is equal to EF. So if you know those things, right, in advance, then what do we conclude by crossing over? We conclude, therefore, AB, the distance between A and B is equal to the distance between E and F. Okay? And we have just crossed over that CD altogether. We just went straight from here to there because those distances were all the same. Okay? All right. All right. Now, we've got some properties here, right? Reflexive, substitution, the transitive. We also have the subtraction property of equality, the addition property of equality. And now we're going to do flowchart proof and two-column proof, paragraph proof, and we're not going to do a construction proof right now. Okay, we're going to skip over that. And then we're going to take a look at some theorems that you're going to practice with, okay? And we're going to try to get through all of that right now. So let's start first with our flowchart proof, okay? So remember that the one thing I would say, maybe I'll start here real quick on this page. You might remember that what we've done before is said, okay, you know, we know that we're from P we are going to Q, or we would say P tells us or implies that Q is true. So if P is true, then Q is true, right? So P implies that Q is true. But somebody might say, well, why? You know, so in here is our reason that we give. So a lot of people like, oh boy, reason. Okay, that's probably, this is all probably really bad here. But a lot of people like the P arrow Q thing. As long as you give a reason, you can move from P to Q. So a flowchart proof is popular for a lot of people because it's a way for us to show, I know this, and it leads to that. right? It leads to this thing. And all I need to do to make that happen, to go from this fact that I know to that fact that I know, is I have to give a good reason, right? So flowchart proofs do that, okay? So let's take a look at an example down here. I'm skipping past the stuff here because here we're seeing examples of the reflexive property and the transitive property and the substitution property. They're all just given examples in there. But here we have a couple of some really good things in here, and I'm going to try to actually see if we can't fill some of this stuff in pretty good, okay? Oops, let me take that off. I didn't mean to have that going there. All right, so, and I need to really quickly edit this document so that I can get my text in here. I want to add some text. So here it says, the diagram shows 4 collinear points. So I have A, B, C, and D. And what they want us to do is they want us to begin by identifying the given and the proof from this conditional statement, okay? So looking at this conditional statement, it says if segment AB is congruent to segment CD, then segment AC is congruent to segment BD. So let's just write in our given statement, which is going to be the hypothesis right here, right? So we would say segment AB is congruent to segment CD, and then our proof statement would be segment AC is congruent to segment BD. Sorry. Okay, and I'm going to just stretch that out just a little bit. Okay, so if segment AB is congruent to segment CD, then segment AC, which is from here through there, is congruent to segment BD. Okay? So now, this is where you're going to pause the video for a moment, and you're going to actually get the scissors out. So we have some scissors over there in the box, and you're going to clip out these actual steps, and we're going to put them in order so that they actually make sense. And here on page 176, you're going to paste them. But I don't want you to paste them permanent until we've checked them. You're going to check with Mrs. Nava. Now the idea is that you want to get from our given statement. So our given statement was this: segment AD is congruent to segment CD, and it's right here. So I can tell you you're going to start with this, okay? And then you're going to finish with this: segment AC is congruent to segment BD. So you're going to finish with this one right here, okay? And what I'm going to have you do is just take a few minutes here and, again, cut them out. And then when you're done, you're going to go ahead and you're going to, you know, put them in order and, you know, show them to Mrs. Nava and see if you think you have them in the right order. And then once you do, what we'll do is we will, I'll go through them and see if you have the same order that I do, okay? Okay, so go ahead and do that. And you can draw arrows. It says arrows connect the boxes in flowchart proof. We've got the box with the given, and then the arrow tells us where what it implies, where it takes us to, right? So you're going to draw some there and, again, lay them out on this page. Okay, go ahead. I'm going to have you pause the video now. And when kids are done laying it out the way they think it should go, you can hit take the pause off, and I'll go through it with you. Make sure you have it right. Okay, so did you go through these and just kind of figure out what you have here? That's, I think, the beginning place, right? So here, this is obviously where we're going to start, and it says that segment AB is congruent to segment CD. And that would be our given in here, right? So this only works if these two pieces are congruent, right? So we know, like, our first step right here, if I was going to just do a, I don't know, let's try that again. You know, if I was doing a step that said segment let me try a capital there. Segment AB is congruent to segment CD, right? That's really just this little bubble right here. And that was given, right? So what does that lead to? I'm going to draw a little arrow here like this. And what would be the next bubble? Well, let's take a look at these, all right? Here's one right underneath it. And let's think about what this says. It has the little M in front of the segment. And it's changed. It doesn't have anymore the congruent symbol. Instead, it has M of segment AB equals the M of segment CD. So really all this is saying is that the measure of the segment AB is equal to the measure of the segment CD. So if I know that they're congruent, doesn't that mean that they have the same measure? And if I'm depending on this definition of congruencies, right? If I'm depending on what it means to be congruent, then it would make it clear that the reason I'm going to give is this definition of congruent segments. So the only thing I need to know that their measures are equal is I just need to know that they are congruent. So that's the next thing I'm going to say. The measure, I'm going to say measure of segment AB is equal to the measure of segment CD. And that's just, like it says, the definition of congruent segments. So I can say that now based on just knowing that they are congruent, right? All right. Now let's look at this next bubble right here. What does this next bubble say? Well, if I look at it, I can see that it's using the measure of AB, right? And using the measure of CD, saying those measures are equal to each other, but it's changed somehow. So always it's a good idea to kind of look and see how things are, changed. And it looks to me like the thing that's changed here is that I've added BC to both sides. And then it tells me that I'm using the addition property of equality. So in other words, I've got the exact same statement, and all I've done is add the same thing to both sides. And all I have to do in order to do this is I've got to show that the measure of BC is equal to the measure of BC, which is this property over here. So I'm going to go ahead and put this one. So this one goes right underneath that one, right? Because it doesn't need anything else. But here I'm going to throw in this other guy. And so the way I'm going to do this, I'm going to go like this so you can see I'm moving this one over to the right a little bit. And I'm going to say the measure of segment BC equals the measure of segment BC. So it's equal to itself. And I'm going to just stretch that out a little bit. And just to show that my box would be kind of off the other direction. And then I'm going to draw my arrow pointing back. So this is kind of funny looking. So I can't just lay my box out. Sorry. So I'm going to just draw the arrow this way. In other words, if I know this, that the measures of AB and CD are equal, and I know this, that BC is equal to itself, using both of those boxes, this one can just start on its own because that's the reflexive property, just say something is equal to itself. But I would use both of these together to now make this statement here by the addition property of equality. So you should have the measure of AB. I'm just going to skip writing the segment part just to kind of save a little space here. The measure of BC, and we should have the segment though because we're talking about their measures, right? So that is equal to the measure of CD, segment CD plus the measure of segment BC. Okay, so now all I've done again is I've added the same thing to both sides. And so, oh, sorry, I didn't put over here. The reason for this was, the reason we can make this statement was just saying something is equal to itself. That's the, let's not forget, that's the reflexive property. of equality, right? And now, what's my reason for making this statement? Well, it would have to be that I am using the addition property of equality. So you would see that here, and you saw that there, the reflexive property. So what does that tell me, right? What does that imply or tell me? Well, notice I'm adding together two segments. AB and BC is being added together. So AB plus BC, what does that equal all the way together? Isn't that equal to AC, AB plus BC? Remember yesterday when we talked about the segment addition postulate, we said if B is in between A and C, then AB plus BC equals AC, right? That was the segment addition postulate. So my guess is that we have, and there it is right here, the segment addition postulate. So we're going to say, you know, that we know that the measure of AB, segment AB, plus the measure of BC, segment BC, equals the measure of AC. So this information here we can now use, and it would imply that this is true, and that is by the segment, I'm going to put SAP, which is the segment addition postulate, right? But that's not all. We're not done yet. Because we can see also that we have CD plus BC, and we're going to say CD plus the same thing BC. What would this be equal to? Again, C is in the middle between B and D. So therefore, if I'm adding these two pieces together, CD plus BC would be equal to BD, right? So that's what we want to state, and that's this guy right here, right? BC plus CD equals BD. So I'm going to go over here, and I'm going to show this would be a separate bubble also, right? Measure of BC plus the measure of CD equals the measure of BD, and that would also be the segment addition postulate, right? So I'm just adding together the pieces. So these two both come from this one statement. If I know this one statement is true, and then I know these pieces are true, then I'm going to use all of this information real quick here. So let's see, segment addition postulate, and then I'm going to go over here, and we're going to use both of those pieces of information. So that's why you see me, I'm kind of laying it out this direction. Okay. Okay, and what are we going to say? Since this is equal to AC, right, and this is equal to BD, and they are equal to each other, can I now substitute AC in for this part and BD in for that part? And that would be yes. So I would have the measure of AC is equal to the measure of BD, and that is the substitution property. Okay? And since their measures are equal, what does that tell me? If I have two segments and their measures are equal, what does that mean? So it means if their measures are equal, it means that they are congruent segments. And so that's where I'm going to go next. I'll say segment AC is congruent to segment BD. Now notice, we were talking about the property of measurement. Now we're talking about the segments themselves. And we're changing from the property of measurement to the objects. Remember we talk about in geometry we have objects and then we have their properties. So whenever we're moving from, oh, I know something about an object and now I want to talk about its properties, then we're usually using the definition of that object, right? The same thing is true when we go backwards. If I know that the properties are equal and I now want to use that information to state that the objects are congruent, then I would say, okay, let's go backwards, right? And say we're going to use the definition of congruent segments to say because the properties are equal, now we know the segments are congruent. So that would be our last statement here, the definition of congruent segments. And I'm going to do a couple things here now. Okay, I'm going to just, first thing I'm going to do is I'm going to draw some lines out to make sure you can check and then have you guys glue in your answers or whatever. But I'm going to do a little arrow, right? So this tells me that that is true, right? And this and this, right, tells me that this is true. Okay? So, in other words, I started with this statement here, then I used this statement here, then I made this statement here on its own. It didn't need any introduction. I could just say that. And then I used that statement to make this statement. These two together to make this statement. To show, hey, I have an equal. Remember I told you that the addition property requires two things. We have to have an equals or an equation, and then we have to have something that's equal to itself that we can add to both sides, right? And now we have a couple of others that actually can be done on their own. The segment addition postulate doesn't need to be justified, okay? Just given the image that we have, we know that point B is between A and C, so this is the segment addition postulate, and that's the same down here. So these guys don't need any arrows leading to them, but because these two statements are true and because this statement is true, we're substituting. Now I'm gonna go with a slightly smaller arrow here, right? So where did I substitute? I took this thing and I substituted it right here, and I took this thing and I substituted it right there. Okay, but you don't need those arrows there. Okay, you don't need to have those. Okay. All right. Oops. You do want to have the other arrow right here. These three you do need together, right? And then I'm going to change colors. I'm going to go a different. I'm going to go up this other direction, and I don't want to get all these arrows confused. So this tells me that this is true. These two things tell me that's true. These three things tell me this is true. And this thing tells me that's true. And with this, you're done. That's the proof. So let's talk about objects and properties again real quick, okay? I'm going to try to go to this blank page and maybe try to draw out for you a couple of things. Let's see if I can make this work okay. Okay. So in this case, I'm going to, let's see if I can make a little, a box real quick. So what I wanted to do real quick is I wanted to, talk about objects and properties. Okay, so I'm going to just do this. Okay, and I'm going to start up here and just write the word objects, and then over here write the word, oh, what happened? There it is. Over here I want to write the word properties. Okay, and I'm going to just slide that in the right place there. So objects and their properties. So over here, okay, an object could be like a segment. So how do we, what properties does a segment have? Well, a segment has the property of measure, right, or length, right? And then we have angles, right? So what property does angles have? Angles have a property, move these guys, huh? I should be moving these. This guy, can't move that guy anymore. Should have moved him before. Well, angles also have a measure. Alright, let's see if it shows up for me. They also have a measure, right? So we have segments, we have angles, and notice that these are properties. So what I want to do is I want to show you that oftentimes in a proof, like this last one that we just had, we want to go from saying, oh, they're congruent. If the segments are congruent, then that means that we have a measure, the property of measure is equal. And we want to sometimes go back the other way and say, well, but if their measures are equal, then we have a, it implies that the segments are congruent. Okay? So this is kind of important. I think that what you're seeing is you're seeing, like P implies Q, but Q also implies P. Right? And we're going to try that over here. Same thing. If an angle is congruent with another angle, that means that their measures are equal. And if the measures are equal between two angles, that means that the angles are congruent, right? So this is bidirectional, okay? And I'm going to try to write this out. Oh man, I hope I can write it good, all right? But remember how we said that P implies Q? Oh boy, that's really bad. So P implies Q, right? And we have this arrow. But whenever we have Q implying P, it's like we have another arrow, okay? And what that thing is called is it's called the biconditional, right? Because it doesn't just go one direction, all right? It's not just a conditional statement that P implies Q, but it goes backwards also. And the biconditional is what we used for, or what we use for definitions. So pretty much any time in any proof when you're going from, hey, I know that this object has the same property, of measure, right? Because the objects are congruent, that means their property of measure is equal. And when the property of measure is equal, that means that the objects are congruent. So anytime you're using that, you're using the definitions. So for example, in this case, we would be saying, oops, let me get back where I wanted to be. So we would be saying congruent, from congruent segments to equal measures would be the definition of congruent segments, right? And we would also say, same thing with congruent angles, right? If I'm going between congruent angles, oops, and their measures, that would also be the definition. You know what I really should do? I need to bring this down here. Hopefully this thing will the whole thing will fit. Let me try sliding that up a little bit. So if I'm going back and forth between either direction, from the definition of congruent segments to the fact that they have equal measures, then I'm using the definition of congruent segments. And the same thing with angles or any other object. When I'm saying, oh, the object is congruent, then the measures must be equal. That would be the definition of, in this case, congruent angles, right? And this would be true, for really any object. So if I want to say triangles or whatever, I've got congruent triangles, then that means, oh, their measures must be equal, because that's what it means. That's the definition. So we're using, congruent objects. So anytime I'm talking about congruent objects having equal measures, then what I'm using is the definition of congruent objects. And I can go either way with it, right? I can go from this direction, knowing that they are congruent, to that direction, stating that they have equal measure, or the other direction, from the equal measures, I know the objects have equal measures, and therefore I'm going to go this direction and say that means that the objects are congruent, and they both get the same exact reason, right? That the objects must be congruent. Again, that's segments, that's angles, could be circles, it could be any objects that are out there, like I said, triangles or something like that. They're always going to have that definition of congruent objects as the reason given. Okay? All right. So that is a lot there. Hopefully you got that. If you need to pause it and write some of that stuff down, that'd probably be good. Okay? And again, that's how we went from objects down to measures using the definition of congruent segments. And then from objects, or from measures, here I know that the measures are equal, and I wanted to go back up here to talk about the objects, and the reason I gave was the definition of congruent segments. So going that direction, I had to give, again, the same reason. From properties to the objects, I'm going the other direction. Okay? All right. So now, here it says you can assemble them, but let's just talk about this second kind of proof here, this two-column proof. Okay, so the two-column proof. So with the two-column proof, we've been kind of looking at those in class a little bit. But basically, yeah, I guess you couldn't print it on this page because this is probably the back of that page, right? 175, 176. So once you cut them out, sorry, I guess you realize this probably hopefully ahead of me, but you assembled it on this page. Paste it in there. Go ahead and get that paste. In fact, I'll pause so you guys can paste the whole thing in now. Okay, so now you're doing a two-column proof. That's the thing that comes up next, right? Two-column proofs are written like this. Here we have the two-column proof. It has all the statements written on the left and all the reasons given on the right. And here's what it says. It says, it is a proof in which the steps are written in the left column and the corresponding reasons. Now, corresponding means the reasons that are attached to the steps, right? So remember up here, when you have your reasons or your statements, underneath the statement is the reason, right? So what I want you to do is you're going to split those up, right? So the statements are going to go on the left and the reasons are going to go on the right. So let's pause it there and you can go ahead and do a two-column proof here. Okay, you can do a two-column proof, and really this is not anything new, but this is just take apart the statements and reasons that you have and write them out. And then Mrs. Navas, when she's done, or when you're done, she's going to check and make sure that you've got these done right, okay? And then you can press play. Okay, so here we go. I'm going to start with our first statement, right? And statement number one was the given statement. Almost always is the given statement. So we're going to say that the first statement, sorry. All right, let's try that again. One, the first statement was that segment AB is congruent to segment CD, right? And then statement 2 is the measure of segment AB is equal to the measure of segment CD. And then statement 3 would be that I know we said that the measure of BC, so the measure of BC was equal to itself, right? And then we said that the measure of AB plus the measure of BC was equal to the measure of CD plus the measure of BC. So these two are equal to each other. This is equal to itself, right? And now we're adding that to each side of that statement, right? And then we're going to say that the measure of AB plus the measure of BC equals the measure of AC, and the measure of CD plus the measure of BC. Oops, I can see that I didn't put measure in here. All right, this is not going to look as good as yours should, hopefully. The measure of BC is equal to the measure of BD. I think the way they wrote this, they turned this around a little bit. They said BC plus CD equals BD, but it's the same thing. And then what are we going to do? We're going to write the measure of AC is equal to the measure of BD. And then step 8 would be that segment AC is congruent to segment BD. Okay? And now let's give our reasons. How could we make all of those statements? Well, the first reason, oh boy, what's going on here? Need to grab that and stretch it out a bit. Okay, so let's go back here. 1. So the first reason, we said that first thing because it was given to us, right? And then we said the second thing, right? If we knew they were congruent, then that means the objects are congruent, and that means the properties are equal. Then we should be using the definition of congruent. In this case, we're talking about segments, right? And then here we're saying something is equal to itself, which hopefully you remember is the reflexive property. Right? And then here we're taking segment, or the facts that we have in line 2 and line 3, and we're adding BC to both sides of line 2. So that's the addition property of equality. Remember that a good proof, the best proof, will give the reasons in the steps. So I'm using step 2 and step 3. Right, step 2 was the original statement, and step 3 another original statement, and I used those two together, right? So if this and this are true, then I can make this Q, this statement right here, 4, right? And then we have, let's see, I'm going to move this, try to get it lined up just a little bit better. Line 5, now in the line 5 I'm saying add A, B, and BC together, and it's equal to the AC, the whole thing, so that is the segment addition property, or SAP, right? In the future, we're going to use this enough times that we're going to start making SAP acceptable, but for right now I'm still writing the whole thing out so you don't forget what it is. So it's the segment addition. Oh, it's not the property, it's the postulate. Oh boy, I am embarrassed. I might have written property up there, and it's not. It's a postulate, right? In other words, it's one of those things, right? When we talked yesterday about Euclid, Euclid said that, let's see, he was saying that certain things can be stated without proof, and we called those postulates, right? That's one of those things that we did. Okay, so then we did the substitution property of equality, and that was lines. So we used this line here, line 4, and what we substituted in on the left was part 5, right? What we substituted in on the right was part 6, right? So we used lines 4, 5, and 6. We used all 3 of those lines there. Okay. And then our last statement, 8, since these segments had the same measure, right, their property of measure, now we want to talk about the objects themselves, so that would be, again, moving between the properties of an object and its object would be the definition of congruent segment. Same thing that we used up here to go from objects to properties, and now from properties back to objects, and that's the definition of congruent segments. So it's a segment addition postulate. Did I put the segment addition property here? Oh, I hope not. Oh, I just put SAP. Okay, good. Sorry about that. I just got a little scared. I probably said it wrong because it wasn't in my mind to call it a postulate before. It was probably saying the segment addition property. But that's one of our 3 postulates that we've learned so far. The linear pair postulate, the segment addition postulate, and the angle addition postulate. Okay? Alright, a paragraph proof is a proof in which the steps and corresponding reasons are written together in complete sentences. So let's see if you can write this out as a proof. So I'm going to try to write this out, or as a paragraph. So I would say, you know, in some kind of a sentence, because segments AB and CD are congruent, their measures are equal. The measure of BC is equal to itself by the reflexive property. Therefore, the measures of AB plus BC are equal to the measures of BC plus CD. I also know by the segment addition postulate that AB plus BC equals AC. Now I should be writing segment AB plus segment BC, or the measure of segment AB plus the measure of segment BC equals the measure of segment AC. But I don't have those tools right here on this calculator. So if I was doing this on the board, I'd be writing M, and I'd be putting the segment symbol over these letters here, right? And I also know, that, let's see, BC plus CD equals BD. By substitution, I can now say that AC, or the measure of AC, equals the measure of BD. And that's really what I should be doing. That I'm going to just write MAB plus MBC equals M. That means the measures, right? And M. Now, I didn't do that above, but above I used the word measures, right? I said equal to the measures of. So I can now say that the measures of AC and BD are equal, and based on the definition of congruent segments, well, I'll use lowercase here, segment AC is congruent to segment BD. Alright, that's a paragraph proof. Notice that this is just my words. If you write your own words out, they're going to look different, right? They're not going to look exactly the same. So don't be surprised. You should, we're really not going to write a lot of paragraph proofs, really. We're basically not. But, when you do, if you do get to a point where you're writing out a paragraph proof, and sometimes we'll leave it up to you, and if you choose, you could do a paragraph proof. But basically, if you do write a paragraph proof, then it's going to be okay for you to put it in your own words. Just write complete sentences, and just explain it. You don't have to use fancy words like therefore, but you do need to use the language that we've been learning, like segments and congruent and measures and equal, and the right terms in here, right? Reflexive property or segment addition postulate, whatever, okay? You're going to need to say those things in any kind of proof, whether it's a paragraph proof or a 2-column or a flow proof, whatever. Okay? Construction proof, and I said we're not really going to do that in here, and that's because with me being gone, it's just a little hard to do. But basically, let's talk about constructions a little bit. Right? You'd start with a starter line, right? We would start by marking off AB. So we would say, okay, here's A, point A. Let me do a freehand here, just a second. So, and I'm going to make this a little bit bigger here. So if this is point A, right, and then I would measure point B. So there's B. So I'm going to duplicate that right here. So there's AB. And then I'm going to measure with my compass, set my radius to the same as BC. So then I would go ahead and set my radius for BC and marks, BC here, right? Oops. And then I could do the same thing only this time I would probably go this direction. I'd call this D, right? And I would measure this, and I'd mark, oh, here's C, right? And this could be B. I should probably, oh my gosh. So Mr. T is not real proud of himself right now. But that's why we don't like to do this using these tools. So this would be really A prime, because now I've moved it, right? And by construction, I've changed where it is. So this is A prime and B prime, and this would be C prime, right? And now I'm going to go D prime here, but this is the second time I'm moving C over here, so this would be like C double prime, kinda. Okay, I'm actually just making a second copy of C here, and then I would put a second copy of B right here, and I would measure that, and I would show, hey, if I started with BC and then I added CD to it, right, I would have exactly the same. It'd be still from here to here, and that's proof by construction. So if you use construction techniques, you could do that. Now, in our class, we are not going to be doing really any proofs by construction. It's just what you need to know is you can create an object with specific properties using only a compass and a straight edge. So that's what it means there. Okay? So we are going to, let's see, I'm going to scroll down now. Here we have another proof. It says the proof of the right angle congruence theorem. So Carl insists that this one in figure 1 is bigger. The angle in this figure is larger than the angle in that figure. And Roy disagrees. He says the angles are the same size, so who's correct? So a lot of kids like to look at the length of the ray. So this is a ray from here down to here, right? And the ray over here. They say, well, these rays are larger than these rays. These are only short. Therefore, this angle is bigger than that one. That's not true. The length of the ray, both rays go indefinitely, right? They go on for infinity. That's why these arrows just show that they keep going. In one case, we represented them by going further than the other, but the reality is they both go the same distance, right? So, and what's furthermore, we don't measure or we don't define an angle by the length of its sides, right? An angle is not defined by the length of its sides. An angle is really only defined by its measure, which is the number of, in this case, we're just going to say it's the number of degrees from one side to rotate to the other. So if I was going to take this and rotate it down until it laid on top of that, how many degrees down would it have to come, right? In both cases, they're marked right here that they are right angles. So if they have 90 degrees, they're right angles, they're both 90 degrees. Therefore, if their measures are equal, then the two angles have to be congruent. And that's what we're going to go into here. Proof of this right angle congruence theorem. It's a theorem that says all right angles are congruent. And you can see that we have all the statements laid out here. So given that ACD and BCD are right angles, can we complete this proof? Okay, so let's go ahead and do that here. So how do we know that angle ACD is a right angle? Well, wasn't that given, right? So we're going to put given here, right? And maybe just move this thing right over here underneath. How do we know that BCD is a right angle? Angle BCD. Well, that was also given, right? So we've got those two given statements there, right? And now we know it's a right angle. Now we're saying its measure is 90 degrees. So going from the object to its property of measure, and that is the definition of a right angle. And we're doing the same thing here. We're talking about the object. Now we want to talk about its property of measurement. So that would again be the definition, right angle. Okay. So if this is equal to 90 and this is equal to 90, what can we say? Right? So this would be the transitive property, right? This equals 90 and that equals 90. So remember, we said like if one is equal to something and that same thing is equal to something else, then they're equal to each other. We can cross over. So this is going to be the transitive property here. All right. Another way you could also do is you could do substitution. Since this is equal to 90 and that's equal to 90, I could take the measure of angle BCD, and where I see 90, I could take this right here and I could plug it in right there and I'd get the statement. So if somebody wrote the substitution property here, that would not be wrong. You can write it really either way. Now look, I've got the measures of two angles are equal, and look at this next step. We don't have the equal sign anymore. Can you see? We've got a congruent sign. So we've stopped talking about the measures of the angles, and now we're talking about the objects themselves. Right? Told you you're going to use this a lot, right? If you go from objects properties back to a discussion about the objects, you're using the definition of congruent angles. Right? You're going to be talking about, from this case, since they are congruent, then their properties of measures are equal, and the other way is true, it's bidirectional. Because the angles are equal in measure, then they are congruent, and that is the definition of congruent angles. Okay, we've got another one here, congruent supplement theorem. So the congruent supplement theorem says, hey, if two angles are supplement of the same angle or of congruent angles, then the angles are congruent. So 1 and 2 are supplements, 3 and 4 are supplements. So that's what we're going to write in here. Use the diagram to write the given statements for the congruent supplements, right? So we're going to say, let's say, angle 1 is supplementary to angle 2. And down here we'll say, angle 3 is supplementary to angle 4. And then the next thing we're going to do is we're going to say that 1 is to 2, and they want us to prove that 1 is congruent to 3. So the other thing we have to know is that 2 and 4 are equal to each other. So we're going to say angle 2 is congruent to angle 4. So if we know these things, that 1 is congruent to 2, 3 is congruent to 4, and 2 and 4 are, 1 is supplementary to 2, 3 is supplementary to 4, and 2 and 4 are congruent to each other, then angle 1 must be congruent to angle 3. So before I go on to actually doing this, let's just go over like how this would actually work, right? So in this case, let's look at what this says. It says these two together, right, are supplementary. That means they measure 180 degrees, right? And what about these two? Well, it says these two are supplementary, and they measure 100. That means they measure 180 degrees, right? So they are together 180, together 180, and then change colors here for a minute and get something kind of over here. This part right here, see this? Oops, sorry, not that part. Sorry, this part right here, the one that's in the box, right? Angle 2 is congruent to angle 4. So if this is x, right, we'll just say for a minute, if its measure is x, then 4 has to also be x, right? So what does that tell us about angles 1 and 3? Well, angle 1 would have to be 180 degrees minus x. It's all 180 degrees except for the x part, right? So minus x. And what about angle 3? Because it's 180 together with x, so it on its own has to be equal to 180 degrees, right? 180 minus x. So what do you notice? Well, they're both equal to 180 minus x, right? So they have to be, that's the statement there, they have to be congruent to each other. They have the same measure. So they have to be congruent, okay? So basically, we've gone over the logic of it here. Now we're going to pause the video again, and you're going to cut out the steps for this and try to work your way through it. Okay, you've got 3 given statements, so you know you're going to have to lay those out right next to each other, and there you're going to be drawing arrows. And I'm going to pause the video one more time and let you work on finishing putting those together on this page. Let's see, this will be on page 183. Put them together on page 183, and then I'm going to have you do your 2-column proof of it, right, where you split the statement on the left and number it and give the reason on the right with the number. Okay, and then think about if you can work on the congruent complement theorem. So now instead of them adding up to 180, they're going to add up to 90. So think about that and draw that out. See how far you can get with this. And I'm going to pause it, and we're going to do some arrows, and we're going to leave it at that. See how far you guys get. Okay. All right. So I'm going to try to draw this out the best I can. I think actually I better zoom out just a teeny bit so we can see that last one here. Okay. All right. Let's see if I can draw this with some arrows real quick. So from freehand, I'm going to go to my arrow tool, and I'm going to get a little bit darker color here. Maybe I'll go with this color here. Okay, so this is saying that angle 1 is supplementary to angle 2. Okay, that means that is a statement about the objects. And what does that mean? Well, it means their measures equal 180, right? So if I add their measures together, it equals 180. How did I go to talking about the object to talking about the properties? Using the definition of supplementary angles. Let's look at the next given statement. It says the angles are supplementary to each other, 3 and 4. So I know that when I'm talking about the angles being supplementary, and then look what I'm doing here. What does it mean that the angles are supplementary? It means, well, that their measures add up to 180. And again, I'm going from talking about the objects being supplementary to talking about what that means for their measures, and I'm using the measures of supplementary angles. Here's a third one. I know that it was given that angle 2 and angle 4 are congruent. So because I know that, what does it mean? Well, if we talk about objects being congruent, and then we want to talk about their measures being equal, it's the, again, definition of congruent angles, going from objects to properties again. So these 3 things here that were given brought us to these 3 facts that we know, right? And now I'm going to switch colors so we don't get confused too much here. Let me go with this color. Okay, so if this is equal to 180 and this is equal to 180, can I take out, let me freehand this actually. So can't I take out the 180 here, right? And because this is also equal to 180, can I then take and put that 180 here, right? So just thinking about that. Right? I'm taking this value and I'm putting it in there because these 2 things are equal. That is the substitution property. So let's go with a green arrow here. This thing, oops, and do the arrow. That'll help it a little neater. So this thing and this thing together allow me to say that if I add the measures of 1 and 2 together, they're equal to adding the measures of 3 and 4 together because they all equal 180, right? So I've substituted and I have this part here. And now if I know this is true and I know this is true here, I'm going to switch colors one more time. Sorry. Let me go with this like golden color here. Because this is true and this is true, look what it says. It says the subtraction property. So what did I subtract? I still have the measure of angle 1 on the left, and I still have the measure of angle 3 on the right, but I no longer have 2 or 4, and that's because those 2 things are equal from each other. So I subtracted 2 from this side and 4 from that side, and by the subtraction property, I've concluded that these 2 measures are equal. So your flowchart, although I don't have the freedom to move these around very well, should be these leading, these brown arrows right here, or whatever color that is, and then those two facts leading here, and then these two facts leading here, which means the last thing we're going to do is, because the measures of these angles are equal, then the objects themselves are congruent. So I'm going from the measures to the objects, and that's why we're having the definition of congruent angles. Okay, so by now you have put together this proof, and hopefully you were able to get that right. And if you need to, you can pause it if you needed help there. But you would have hopefully got that done, and now you can write out the statements. Statement 1, 2, and 3 were those given statements. 4, 5, and 6 are the statements that they implied. And then, keep going from there till you get through all the statements that we used. Okay? And then the congruent complement theorem is going to be exactly like this one, only we're going to be using complements in here instead of supplements, right? And instead of saying they equal 180, we're going to say they equal 90. So we're going to be changing this to 90. But basically, all the rest is going to be the same, right? And for a diagram, instead of showing two linear pairs like 1 and 2, 3 and 4 equaled 180, now you're going to be showing two right angles with, split 1 and 2, and a right angle here, 3 and 4. So you should be able to have hopefully got that done using the same exact approach. And I think that we should be out of time at this point. But if not, I challenge you guys. See if you can figure out how you know that in this case, angle 1 is congruent to angle 3, and angle 2 is congruent to angle 4. See if you can work through that on your own. And if so, that's what we'll call it for a day. Okay. I guess if you're done and you can keep going, you go through problem 7 as well, and the rest of it as needed. Okay. But I think that will have been a pretty good lesson period for you. So see if you can get that far.